It's time now to develop the thin lens equation, as well as what your book calls the lens maker's equation, although really it could be regarded as a single equation. They just take the right side of that one equation and they call that the thin lens equation. And we couldn't do this if we hadn't looked at refraction at a spherical surface in a recent video. So let's go back to a couple diagrams from your book. Here's an image that we looked at recently, exploring the formation of an image or an image point from an object point by a spherical interface between two media. And we looked at the mathematics of this in detail. Using small angle approximation, we were able to show how this image distance S prime depends on the object distance S, and of course also on these two indices of refraction. Well, I don't think it's terribly common to form an image with one interface. I'm sure there are many applications. I can't think of one off the top of my head, but it sure is easy to think of applications of lenses. And a typical lens is just two conjoined spherical surfaces. So the first thing to recognize is by spherical surface, we mean this is a section of a big old sphere, or in two dimensions would just be a circle. And they've labeled the radius R1. So if you were to draw a circle around this point right here, big old circle, just part of that circle forms the front face of this lens. Back here, around this point, if you were to draw a circle with this radius R2, part of that circle would form the back face of the mirror. I say back face because in this picture, the object is over here. Of course, you could put the object over here and also form an image maybe somewhere over here. It works both ways. You've already seen that the focal length is the same on both sides, and we can show that now. So all we have to do is apply the equation that we developed for this picture twice in succession to this picture. And maybe the trickiest thing about this, if you haven't thought about it yet, is that the image formed by the first face of the lens will become the image, I goofed that again, the image formed by the first face of the lens will become the object for the second face. Let me repeat that one more time. The image from the first face becomes the object for the next face. So S prime, that thing that we normally, or the quantity we normally call the image, S prime is going to be S for the second face. Okay, so if this is your object, look at the rays emanating from the object. They're all refracted at this boundary. Those are the solid purple lines here. You can see that they're refracted towards the normal. That's not the only time I'm going to make that mistake. They're all refracted towards the normal, and then they're refracted again at this back surface. Now, if your eyeball was within this glass, that's silly to think about, but if you could somehow collect this light, it appears as if it's coming from someplace back there. So each of these purple lines within the lens, extend them backwards. Whether you're taking a picture in here with the camera or you've got your eyeball in there, it makes no difference whether the rays actually came from back here or whether they emanated from here and then were refracted at this face. It makes no difference whatsoever because all that really matters is the direction that the rays are going. So as far as this face of the lens is concerned, all of these rays, these purple rays within the lens, they really did come from back here. So this image point, this is the image point from the first lens, or from the first face. This is the object for the second face. And you should already note an important difference with the diagram previously. Here, they're imagining that these rays are converged enough, or they're refracted enough that they actually converge and form a real image inside the material, in which case S prime is considered to be a positive number. Remember, image distance S prime is always a positive number if you're talking about a real image. In this case, no rays actually converge back here. They only appear to diverge from there. That's considered a virtual image. So this object, this image distance, S1 prime, would be a negative number. So S1 prime for the book, that's the image for the number one face, the first face of the lens. All right, I think we should jump into the mathematics here, but we're going to have to talk about the thickness of the lens, and this is the overall final image. After we've written down some equations, we will dispense with the thickness of the lens by just pretending that it's a very small number. In other words, we're talking about a thin lens. And then we can just deal with a single object distance and a single image distance. So let's do that. And for starters, we're going to need the equation that we developed in the previous video. Image formation by a spherical surface, spherical interface, boundary, whatever. Let me see if I've got that memorized. I believe it was N1 over object distance plus N2 over image distance equals 1 over R times N2 minus N1. I'm not going to check that in the book. I'm pretty sure that's it, and I will proceed accordingly. And if I'm wrong, it just means this whole video will come out wrong, and then I'll have to re-record it. But that's not your problem, is it? Now, as we go through this, don't forget that this quantity R, the radius, it has a sign associated with it. It could be a positive number, and it could be a negative number. There is a sign convention that you have to bear in mind. First, let me draw the optical axis. Your book refers to this thickness as T. And you can see how the front face is part of a circle, the back face is part of a circle, and I'll just label this R1. What kind of a number is R1? Well, you have to consider the direction in which the light is coming or moving. This face of the lens is convex towards the object, convex towards the object, and that means that we have to use a positive number. R is considered to be positive if the curved face, the spherical surface, is convex towards the object. This face is actually concave towards the object. Now, I'm already realizing, are we supposed to ask if it's concave or convex towards the actual object or the image from the first face, which we treat as the object? And that's kind of a crucial question, isn't it? I believe it's, you would go by the thing that's actually acting as the object for the second face. That'll make sense when we get to it. Okay, so if your object is here, I'm not even using a ruler here. This ray, see, now I'm a hypocrite for saying that you were a bum if you weren't using a ruler. This ray would look like it was coming from somewhere back here. Okay, if you look back at the publisher's image, you'll see why my drawing was no good and I had to start over. Actually, I had to start over a couple times, but this diagram should work. This doesn't look like a thin lens, but we have to make it a little thicker so that we can actually visualize what's going on. The distance from the actual object, if this was the flower that you were looking at, from the object to the first face of the lens, that's the object distance S1. And because of the refraction at the first face, in this case, we've got a virtual image. These rays are not actually converging over here. They appear to be diverging from here. I say these rays, but I've only drawn a single ray. If we had another ray coming in, getting refracted, it would also appear to be coming from back here. So this is the image distance for the first refraction. Notice we go from the image point, not to the middle of the lens, but to the front of the lens. We call that S1 prime. What kind of a number is that? If it's a virtual image, the image distance is a negative number. This image, the image from the first refraction, serves as the object for this next side of the lens. Remember, this face of the lens doesn't care where these rays come from. It only cares about the direction of the rays. So we need this distance from previously what we called the image, which is now the object for the second face, all the way to the right side of the lens. And that would be the absolute value of S1 prime. Remember, S1 prime is a negative number, absolute value plus the thickness of the lens. And then finally, the image distance from this second refraction is this length. We'll call that S2 prime. And all we have to do is apply our previous equation twice, once for each spherical interface. So for the left face, what do I have? I will call this, just as your book does, we'll consider this to be air, and this is just some sort of glass, usually, with an index of refraction of something like 1.5. I'll just call it N. This is also air. So the index of refraction on this side is 1, and on this side is also 1. So if you look back at the equation that we've been using, adapt it for the refraction at the left face, instead of N1 and N2, we're talking about 1 and N. 1 over the object distance S1 plus N over S1 prime. This is object distance, image distance for the first refraction. That's got to be 1 over, well, R1 is the name of this particular radius of curvature, 1 over R1 times N2 minus N1, but my N2 and N1 are just N and 1. All right, so make sure you see how this came from the previous equation. As for the right face, well, one thing I should note here, isn't the absolute value of -3, 3? In other words, it's the negative of -3. So we could write this as negative S1 prime plus T. Taking the absolute value of S1 prime is the same thing as just sticking a minus sign in front of it. Now, this is my N1 and this is my N2 for the second refraction. So I would say N over the new object distance plus my index of refraction on the other side would be 1 over S2 prime. That's got to equal, well, the radius of curvature for this spherical surface is what we're calling R2. And now my second index of refraction is 1 and my first is N. The order is flipped from what it was over here. Here's where we can use the fact that the object distance for the second face of the lens is this junk right here. Okay, so N over negative S1 prime plus T plus 1 over S2 prime. Nothing else changes. All right, what are we supposed to do with this? We are going to combine these two equations. And the first step in doing that is to recognize that for practical lenses, very often, this number is inconsequential compared to the other distances involved. You know, you may have a homework problem or perhaps even an exam problem where you're dealing with a lens of a finite thickness. Well, every thickness is finite, but maybe the thickness is significant. If T is much less than the original object distance and the final image distance, then you're validated in using the thin lens approximation. What is the thin lens approximation? We just pretend that T is 0. So if we let T go to 0, we've got an N over negative S1 prime here. We'll check it out. N over negative S1 prime, N over positive S1 prime. Let's add this equation to this equation. Add the left sides together, add the right sides together. When we do that, these two terms will cancel on the left side. So I'll say after adding the two equations, what's left? We would have 1 over S1 plus 1 over S2 prime. This is the This is the object distance for the left face of the lens. This is the image distance for the right face of the lens. What do we have on the right side after adding these together? Well, I actually have a common factor of n minus 1. Couldn't I change this to an n minus 1 instead of 1 minus n if I pick up a minus sign here? Right, 5 minus 3 is in the negative of 3 minus 5. So I will factor out n minus 1. And I've got the positive 1 over R1, and then the negative 1 over R2. That was really easy. We're basically done here. Let's look back at the picture. It's no longer necessary to distinguish between values of S for the left face and values of S for the right face. Let's just regard the whole thing as a single optical element. It's a thin lens, and we'll use simpler notation. Instead of S1 and S2 prime, remember, S1 prime is how far the object point is from the front face of the lens. But if we're regarding the lens as very thin, we can just say it's the distance from the lens. By the same token, S2 prime is the distance of the final image point from the right face. But if we pretend that the thickness is 0, we may as well just say that's the distance from the final image to the lens itself. So we'll just replace this S1 by an S. This is how far the object is from the lens. This is how far the image is from the lens. N is the index of refraction of the lens. Of course, this equation only works if your lens is immersed in air. That's why we've got these factors, or these ones here. You'd have to start over and write the equation differently if you immersed your lens in water, for instance. Okay, and one of the trickier things about using this equation is to bear in mind the sine of R. If the light from the object goes this way, this lens would be convex towards the object. This lens would be concave towards the object. This would get the minus sign, this would get the plus sign. It's going to take some practice before you get used to that. And you can actually draw lenses of all combinations. This is a so-called meniscus lens. If your light's coming from over here, this would be concave towards, and so is this one. Both of these radii would be negative numbers. You can have something like this, a so-called plano-convex. If the light's, let's say the light's coming from this way, what type of a number is this? Well, this would correspond to a circle with infinite radius. This radius would be infinity, and this side of the lens is concave towards the light. So this would be considered a negative number, or a negative radius. If the light was coming from over here, you would consider it to be positive. Maybe you're thinking, wait a minute, there can only be one number for the focal length. And you're right, but trust me, it all just works out. If you use the equation appropriately, things will work out. All right. And you know what? I think I see right now how that would change. If I focus on this, if the light was coming from this direction, wouldn't this be R1? And this would be radius 2, or radius 1 would correspond to this face, radius 2 would correspond to this face. If I come from the other side, now this corresponds to radius 1, and this corresponds to radius 2. So I would, my sign would flip. I'd have to reverse the roles of these, but I would also pick up a minus sign in R2. So the two minus signs would cancel. It will all work out if you observe the sign conventions. Okay, now let's make one more observation about this equation. We've already talked qualitatively about the behavior of a lens when the rays come in parallel. If you have a whole bunch of rays coming in parallel. The example I gave was the sun. Well, when you focus the sun's light to a tiny little point to light something on fire because you're a pyromaniac, you should see a therapist about that. The object that you're talking about is the sun. You're actually making a tiny little image of the sun. The sun's really far away. It's not infinitely far away. And one of my favorite things to talk about in these classes is the history behind measuring the distance to the sun. That's such an exciting topic, but it's not infinity. It's something like 150 million kilometers, which is still a really, really big number. And if you've played with a magnifying glass, you know that this distance, the focal length, it's just a few inches. A few inches compared to 150 million kilometers, that means that this number is effectively 0. 1 over 150 million kilometers is effectively 0 compared to 1 over 4 inches. So here, if you're talking about rays, a bundle of rays, which really are parallel, you can assume that your object distance is infinitely far away. So we would say here, s equals infinity, and that means 1 over s is effectively 0. So we go back over here. If this is 0, we can just disregard it. And that means that the reciprocal of the image distance is equal to all this, 1 over s prime. And your book actually calls this the lens maker's equation. It comes from the same equation we just developed here. And I have to make one more observation here. This is what we normally call the image distance, but going back to our discussion prior to developing the thin lens equation, if you're focusing the light from the sun to a point, this is a very special image distance. This is what we call the focal length. So s prime, in this case, is equal to the focal length. So I should really write 1 over f. That is the lens maker's equation. I really don't have that memorized. I think you should throw that on your note card. This would allow you to design a lens with a particular focal length. If you know what you want your focal length to be, and you happen to know the index of refraction of the glass that you're working with, these are the radii of the two spherical surfaces that you're going to have to grind down in order to give this lens the desired focal length. So I'm sure in laboratories around the country, every day people are manufacturing lenses where they make use of this equation. Now, the optics that we're looking at here is pretty elementary. You can find this in any book appropriate for this class. You can get graduate degrees in optics, so there's probably some additional considerations here. But this is most of what you would need to make an effective converging lens. And in the next chapter, when we look at optical instruments and corrective lenses for nearsightedness and farsightedness, the reciprocal of focal length is what's called power. So high-powered lenses would have a large value for this reciprocal. That would mean a short focal length. That's worth memorizing now. The shorter your focal length is, the higher the, air quotes, the higher the power of your lens. Lens maker's equation. Doesn't that sound kind of old-timey? It's like a shoe cobbler's equation. Is there a shoe cobbler's equation? I've never heard of such a thing. I know there is a telegraphist's equation. We looked at the wave equation earlier this semester for waves on a string. You can develop a similar equation for the speed at which waves, electromagnetic waves, travel down telegraph wires. It involves inductance and capacitance, and it's called the telegraphist's equation. I like these old-timey names. Okay, well, this is an equality between all this garbage and the reciprocal of focal length. We've established that this quantity is 1 over the focal length. So let's just call it that. And now we can abbreviate that whole equation like this. And this is arguably the most important equation from the chapter. You don't have to remember how to go through all these so-called derivations. You don't have to know how to derive the thin lens equations. That's this equation. You have to know how to use the thin lens equation. That's the practical part. So I will work several of your homework problems from chapter 34, which make use of the thin lens equation. And I'd like to say a few more things about this equation, but you're adding up reciprocals and getting a reciprocal. So find the reciprocal button on your calculator. I've got one. See where it says, you can barely see it, whatever. It says 1 over x here. So if I've got a number like 5, and I want to take the reciprocal, shift 1 over x, I find that useful when I'm solving these problems. A word about algebra here. Let's see here. 1 over f equals 1 over s plus 1 over s prime. There is a little algebraic device that I personally like to use often when I solve these problems. Let me show you something related. 1 over a plus 1 over b equals 1 over c. Those of you who took 3b may remember the formulas for adding capacitors in series. Yeah, the sum of the reciprocals of two capacitances or two capacitors is equal to the reciprocal of the equivalent capacitor. And you may have seen a more straightforward way of evaluating this in your calculator. This would mean that C is equal to the product of AB over the sum of AB. You can check that algebra, but these are equivalent. Now I'm a little nervous about whether I've done this correctly. Let's see, if I add these with the common denominator, I'd have B plus A over AB equals 1 over. Okay, good. Yeah, that works. You can apply the same thing here. F, the focal length would be S times S prime over S plus S prime. I often find this easier to work with because sometimes these numbers are just integers and you can almost do it in your head. So just be aware that there's another way to evaluate that. Very often, instead, we're looking at something like this. 1 over S prime is equal to 1 over F minus 1 over S. See how I solved this equation for the reciprocal of image distance? And if I combine these with the common denominator, I think I'm going to wind up with this. Let's see here. Wouldn't this be S minus F over Fs? Correct. So this would be Fs over S minus F. And at this point, you're likely to make an error. I almost just made an error in my head with the algebra, but you may prefer to do it this way. Or just be quick with the reciprocal button.